Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Concrete Slabs, and it is going to provide you fundamentals of the yield line method and also the automated yield line method. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the topic, and then focus on the traditional handy of the yield line method and the automated method and the applications before wrapping up with conclusions. Have you ever tried to envision the shape that a plate will take under load? Being able to do so is important for understanding how plates work. It is also important for identifying regions with high curvature and moment, and points of maximum deflection. Let's investigate a square plate with simple supports, as indicated by these dashed lines. The white grid makes it easy to see the shape that the plate will take as it is loaded. The curvature is positive, sagging everywhere, and in both directions. You can also see that the maximum deflection occurs at the center of the plate. If we now clamp one of the edges denoted by the solid line, we discover a negative moment hogging along the clamped edge. The same thing would happen if one end of a beam were changed from a simple support to a clamped support. A simply supported plate that spans two bays takes this shape, and it exhibits both positive and negative curvatures. If we remove the center support, we get a rectangular plate, and it takes this shape under load. Notice how the curvature across the width of the plate remains nearly constant until you get near its ends. Notice, too, that the curvature in the long direction is nearly zero except near the ends. If we remove one of the end supports, and the plate deflects like this, and removing the other end supports produces this result. Notice how bending occurs in only one direction. Floors in buildings are often supported by columns in this model system. As you can see, the deflection pattern is quite different from that of a plate that is supported along its edges. And here is a column-supported plate that spans two bays. Suppose we had a floor with an overhang. How do you think it would deform? Here is what the model shows us. Can you understand why the plate takes the shape it does? Understanding plate curvature is especially important in the design of concrete floor slabs. The reason is that concrete, like the blocks in this model, cannot be relied on to carry tension. Consequently, steel reinforcing must be incorporated any place that tension could arise, and that includes the tension side of any regions where bending occurs. That is why it is important to know the direction and the degree of bending at every point in a plate. Okay, so focus of today is on the yield line method, in particular the automated yield line method. But first of all, take you back to the traditional handy of the method. How do we apply it? What is it? Basically, it's a direct analysis tool, where we are looking up the slab simply at the point of collapse. So what we do typically is we guess a yield line pattern. We then equate internal and an external work to determine the collapse load factor, or in a design context, the moment capacity needed to deliver the required capacity. So, pretty simple calculations, that is what the benefit of it. Another key benefit is that you tend to obtain much more economical designs than if you use elastic methods, or in assessment context. You can review your hidden strengths of capacity in the existing slab. The downside is if you're working with a hand method, it's unconservative if you choose the wrong mechanism. So if you miss that critical failure mechanism, you will overestimate the true collapse load. That is a key area that we were able to address. We take the guesswork out of the process effectively. In terms of application, in the 90s and 2000s, co-workers at Cambridge used the U-line effort very effectively to demonstrate that many UK bridges has hidden reserves of strength. So what they did was they compared the elastic access capacity, shown by a red bar, with the plastic access capacity, shown by a green bar, for a population of bridges. In a great majority of cases, the bridges have been identified as being substandard using elastic methods, were actually perfectly adequate when plastic method, U-line method was applied now. The U-line method subsequently proved difficult to computerize. However, we can use the method called Discontinuity Layout Optimization, or DLO for short, to automate the critical U-line pattern. What does the process look like? First at all, we start with a slab. We populate the slabs with nodes. We connect each node to every other node with a potential U-line, and then we use optimization to identify the critical minimum energy solution. So in this particular case, we can use the U-line pattern, indicated by the red and blue U-lines hogging and sagging respectively. Terms of mathematics, basically, you minimize the energy, subject to compatibility constraints and the unit displacement constraint according to the principle of virtual work. The main constraint of interest is nodal compatibility constraint. If we zoom in a particular node, that if we resolve the rotation in the x direction and in the y direction, as we go around the node and come back to at the starting point, those must sum to 0. It's very much akin to force equilibrium in a truss. In a truss, we will typically resolve the forces in the x and y direction, and they must sum to 0. It's the same here, but now we are resolving U-line rotations. Now I'm going to show is actually a floor plate for an apartment floor and was constructed in central London. This is actually the same apartment floor that was considered in the concrete design guide. What they did in that design guide is they used the hand-based U-line method. What they basically did was try lots of different potential U-line patterns in order to identify the critical one and design on that basis. And you can see that one of the mechanisms is kind of falling plate mechanism. It is from one side of the building to the other, and that's what was found to run most critical mechanisms. When we entered the details of the geometry into DLO, actually found that wasn't far off the mark, and actually it is less than 10% lower than the automated U-line method solution. From conclusions, what we learned, the U-line method provides a powerful means of analyzing the ultimate limit state. We have automated it using DLO, which is a linear optimization problem that is easy to solve. You can identify a wide range of different failure mechanism types automatically. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.